Now comes the important fact and the important point, which is the equivalence between that there is an equivalence between autoregressive and moving average models. And we have discussed this, you have already now kind of sensed it in many different contexts, that an AR model can be rewritten as a moving average model and vice versa, right. And in general, if you have an invertible moving average process, right, you can give an stationary autoregressive representation and vice versa, but obviously not of the same orders. In fact, there is now a different way of defining invertibility of moving average models. A moving average model is said to be invertible if and only if you can construct a stationary AR representation. Sometimes you will see this definition in certain texts, that an invertible moving average model is that which allows you to construct a stationary autoregressive representation, right. Because we know that the moving average model can be rewritten as an AR representation, but stationary one. So, if I have an MA1, I have Vk as Ek plus C1 Ek minus 1, and I can rewrite this as an AR in an AR form, that is here I have 1 plus C1 Q inverse times Ek on the right hand side. Now, I can rewrite this in this form and straight away see that invertibility implies stationarity, right. But in the sense here, if it is invertible, the zeros here have to be outside the unit circle. Now, when I look at this here, this is not in an AR form, right. An AR form would be, let me put it this way in fact, so that you see it more clearly. Vk equals 1 over 1 plus C1 Q inverse inverse, you can see even it this way. Either way it is the same thing. If the process is invertible, then you can construct a stationary AR representation and vice versa. But obviously you can see straight away finite order moving average models would have an infinite order AR representation, and an infinite order AR finite order AR representation would manifest as an infinite order MA. You can even imagine this from the ACF viewpoint. When we looked at the ACF of AR models, let us say an AR1, it had an exponential decay, but suppose I did not know that there is this class of models, that autoregressive models exist, I did not know, I only stopped listening after moving average models, let us say in the class. Then I view any process from a moving average viewpoint. From that viewpoint, the AR process will manifest as the moving average of infinite order, because it does not really die down at finite lags theoretically. So, from that viewpoint also you can say that a moving average model an AR model manifests of finite order manifests as moving average of infinite order. Either way, now the question is which model is good, okay, that is the most important question that keeps bugging us, but we will come to that shortly. I am going to skip this, we have already discussed this. Now, let us actually look at the mixed effects model first, and then come back to this question as to which model is suited. So, in general we need not have pure AR or pure moving average models, there can be mixed effects, in the sense that a process may be evolving as a function of its past and also evolving as a function of the past shock waves, both. So, what I am today is partly because whatever I have done in the past, whatever my reactions have been in the past, plus whatever I have been, whatever uncontrollable things have been happening to me. Ek is something that is unpredictable, I do not know, I mean in the sense it is a shock wave. So, there are these unpredictable things happening in my life, they seem to have an impact, plus my own reactions to those unpredictable things in the past. Okay, yes.
That we are having otherwise also.
Sorry?
When we are using an AR model, we are always using a
Correct.
That previous is always determined by that point shock wave. So we are indirectly, we have an effect of that already.
Yes, you do, but then what happens is now whether it is a good question. What you mean, what you are asking is if I have an AR1 model for example, Vk minus 1 cumulatively contains the effects of all the shock waves, correct. But now if you look at the architecture of an Arma model versus the architecture of AR model, Ek minus 1 let us say if I have an AR1, Ek minus 2, Ek minus 3, they are affecting Vk all of them through Vk minus 1, that is the architecture that you have, right. So, it is an indirect way of affecting, but there is this if you look at the architecture of Arma model, what it is saying is the shock wave not only in the past whatever past shock waves, they are not only indirectly affecting your presence, but also directly coming and affecting. They have another propagation path, okay, and that is possible. You can have multiple pathways, right. There is one pathway which is indirectly affecting even now and probably for many instants to come, but then there is a direct pathway as well. When even if you take any physical process and I give, let us say there is some earthquake somewhere, there is an indirect pathway, but there is also a direct pathway, maybe a delayed one, we do not know, right. It can come back and affect, and then when the earthquake occurs, the building starts to crumble and there may be effects of this past shock waves, but then something else also, the past shock waves actually are coming back through some other path and affecting your structure. That may take some time though, right. So, this Arma architecture is different. If you were to draw graphically, and maybe that will help you, for an AR1 the graphical representation would be, suppose this is your K and here. So, here let us say it is K, K minus 1, and then you are standing at K plus 1. Here you have Ek, Ek minus 1 and Ek plus 1 and so on. So, AR1 has this kind of a graphical representation. This is a chain of connections or pathways you can say. Whereas an Arma, suppose an Arma 1-1, in the interest of time I am not going to redraw, suppose you have an Arma 1-1, then what you would have is an additional pathway directly affecting. So, Ek minus 1 directly affects K. What is an Arma 1-1? The model would be Vk is Vk minus 1, well Vk plus d1 Vk minus 1 equals Ek plus C1 Ek minus 1. I have reached the border, okay. Now, there is a direct pathway. Right, and so on, Ek would affect Ek plus 1 directly also. So, there are two pathways, right. So, that is the Arma architecture for you, and the MA architecture would not have these connections, it would not have these direct connections, only these connections, that is it. This will always be present, although we have pulled this out, again I should keep saying this, although we have pulled this out, this is internally a part of the process itself, just for the sake of modeling and representation we pull them out. Is that clear now? So, that is the difference now between, and how do I know now? How on earth do I know how the process is wired inside, right? Nobody knows, and that is the beauty of it. That is, as I always say, it is a good thing that nobody knows, right. I mean that is how you have thousands of papers and methods and so on. So, keep guessing, right, that is what God says, keep guessing, does not matter, it will earn you livelihood and you keep moving on. Even at the end of our lives we would not know, maybe in the soul form we would know, not in the physical form. So, anyway, so when what kind of Arma models do we admit that are both invertible and stationary? You should understand now these two requirements. Stationary obviously is a very obvious requirement. Invertibility you can understand is a requirement because there is a moving average component, and when you were to write the forecast equation, for example, for an Arma 1-1 here, the forecast would involve Ek minus 1, and again I go through the same ordeal of recovering Ek or Ek minus 1 from the past observations, and once again the requirement of invertibility will crop up. So, we only admit Arma models that are invertible and stationary. In other words, even though the process must have been generated by a non-invertible one, I will identify an invertible and a stationary Arma model, okay, which means now the zeros and the poles have to be in some region. If I say zeros and poles in the classical sense, that is in the sense of Z, then they have to be inside the unit circle. Okay. So, when you are given an Arma model, you should check upfront if it is invertible and stationary by examining the poles and zeros. Now, what about the ACF of an Arma process? Again, we are asking this so that in practice I can guess if an Arma model is suited. We have learnt already how to figure out if an AR model or an MA model is suited. Is there a way I can determine whether the whether an Arma model is suited? Unfortunately, you can't. I mean, I am giving you the procedure for calculating ACF, but this is practically of no use. Only it is useful in calculating the ACF theoretically, like your Arma ACF for example, uses this procedure to compute the ACF. If you were to intuitively ask how the ACF would look like for an Arma, what is your answer? How would it look like? Remember, there are a superposition of effects. Yeah, so moving average model, the moving average component will stop contributing after a certain lag, and then the AR model takes over, AR component takes over, and that always results in an exponential one. So, if I have an Arma 1 up to lag 1, you will have both moving average and autoregressive effects contributing. Beyond lag 1, it is only the AR component. And now you can extend this to an Arma P, M model. But what is it? I mean, when I look at the ACF, it is not going to help me in any ways. I can't say, yeah, okay, after this lag I see an exponential decay, forget it, you would, no way. This behavior itself is complicated, and then on top of it you will have estimation errors creeping in.
You would see some kind of step at some level.
Yeah, that is all theoretical, everything is ideal. Idealism is good for dreaming. Correct, you are right. At some point you may see suddenly exponential decay setting in. But how good is the transition? Theoretically itself depends on the orders of MA, AR and the values of the coefficients and so on. And to top this, like in your pizza you have toppings, you have an estimation error which really dominates, and that depends on the sample size that you have. So, there is no way you are going to observe this with any distinction, it is not worth spending that effort, it is not at all worth. So, all these theoretical things that we are studying, at least for AR and MA it is pretty clear, I can get a very good guess, but when it comes to Arma there is no way my ACF or PACF is going to give me any good guesses, because it is so difficult to disentangle the contributions of, decouple the contributions of moving average and autoregressive. Okay. So, what do we do in practice? Trial and error, okay, but in a more systematic manner. This course is not to teach you modeling on a trial and error basis, but in a systematic manner. And we will go through an example later on. I will show you how to fit a model, time series model systematically. But let us ask this question. We have already talked about the order. Let us ask this question on which model do I choose? AR, MA or Arma for a given series. I give you a series, you pick any of the series that you have seen before, which you deem to be stationary, you thought it is stationary. Okay, we have not talked about stationarity tests. Let us say that you are given it is stationary. Which model would you pick?
One of them is finite, then you can choose either AR or both are infinite.
Both are infinite. Let me tell you in practice, nothing like that you are going to see. Only for a few select processes you may see all that nice things. Somebody else had some other answer. Yeah, you will pick Arma.
If MA model is there, then AR process conditions will be
0. Oh, you are hoping that will happen. So, you start away straight away with Arma, over parameterize and see if it works. Do you understand how painful it is to estimate an Arma? The moment you have a moving average model, painful in the sense, yeah, today the computer does it, we are not going to break a sweat. In fact, if you are sitting in AC, not even a drop of sweat. So, but you will not get unique optima, and there are issues, but still there are efficient algorithms for estimating Arma models. But then, why study all of this? If you are going to start off with Arma, why study any of this, right? So, there are some guidelines. So, we cannot give theoretical answers as to, yeah, this is a metric, if, or this is an indicator, nothing like that. As he says, yeah, you look at ACF and PACF, that is the first step always. Now, you see, if you were to fit an MA model, what would be the order? If you were to fit an AR model, what would be the order? That means, and the order will tell you how many coefficients you are going to estimate, right? If it turns out, and if there is no preference for a particular type, if it turns out that an AR model of order 1 or 2 can explain your series, go ahead with it, versus an MA which may take a few more, right, a few more coefficients. And we know why we prefer AR models, because the predictors are linear, and we will learn later on that with the least squares approach or even the Euler-Walker methods you have seen, very easy to estimate. Even recursively, I can estimate AR models over a sweeping, I can just sweep through a set of orders to figure out which AR model is good. In other words, I can look at PACF. With MA, that is not the case. I can't estimate orders just like that. There is no recursive algorithm. So, there is no definitive answer, and the most important thing is there is no model that will give you a true description of the process. That is all a myth. Okay? There is nothing like a correct model. We are only seeking a working model. And what are the principles on which we want to build our model? One of the most important principles is parsimony. Be stingy. This is one place where you want to be really miserly. You want to keep the model as simple as possible. Okay. So, this basically says that in modeling, keep things simple. Since no model is going to be actually correct, why are you actually running after complicated models when a simple model will do the job for you? But you can't keep it simple and simpler. I mean, you can't keep simplifying and say, I will not model anything. You wanted me to keep things simple, right? So, no, what it says is there is always a trade-off involved. As you keep increasing the model complexity, yes, you will get better and better fits, but at some point you will start overtraining the model. You will start remembering all the numbers in the assignment questions also. We do not want that. You only want the concepts to be understood. Leave aside the numbers for the specifics. So, if an AR model of a low order manages to explain, then so be it. In fact, generally when there is no preference for a particular model, one would fit an AR model because it is easy to estimate. On the other hand, it can so happen, for example, if you have a process like this, the true process is an Arma is of this type, 1 plus let us say 0.6 Q inverse over 1 minus 0.7 Q inverse. If we look at, and you can try it out, Arma ACF allows you to compute the theoretical ACF and PACF. You will see that ACF, if you were to look at fitting an MA model, it will be of high order, high in the sense relative to what the true one is, and so for the AR model as well. But there you have to now, as you said, if the ACF decays slowly, PACF decays slowly, so maybe this PACF for this will actually die off only after lag 4 or 5, then you may want to consider an Arma 1-1. At that point you want to consider an Arma 1-1, because an Arma 1-1 has only 2 parameters. For this process, an Arma 1-1 will do the job for you vis-a-vis an AR5, which will involve 5 parameters. From an estimation theory viewpoint, and this you will learn later on, more the number of parameters, larger the error in the parameter estimates. And that is another reason also why parsimony is preferred. Okay? So, always choose that model description which contains a few parameters without compromising significantly on the quality of the predictions. That is, and that is the basis of several information theoretic criteria like Akaike information criteria and so on. Many a times what can happen is an AR2 and Arma 1.1 can actually do the job for you, or the same number of parameters may prevail. So, what do I do now? If the number of parameters is only the guiding principle, what do I do? And that is where the information theoretic criteria comes and tells you, although you have fit same parameters, you can look at the estimation errors in these parameters, because in estimating an Arma model you may have used a nonlinear least squares problem, you may get a local optimum, whereas in estimating an AR model of the same number of parameters, right, or it does not matter how many parameters, you will always get a unique optimum, because it is a linear estimation problem. The parameters can be estimated using linear least squares or Euler-Walker equation. So, you would prefer an AR model in that case. So, there are some guidelines, and that is what we learn through different case studies, and I will go through or a few case studies, but in all of this over parameterization has to be watched out for. Okay. That way, according to your approach, actually I can go ahead and fit an Arma 2020 and then go backtrack, but then you do not know how many you have to turn to be 0, because sometimes the situations can be tricky. When you come back, then some may be non-zero, some may be 0 and significant and so on. So, it becomes very difficult. Always in modeling you want the bottoms up approach, not the top down. You do not want to go to the highest order and then come back. You want to actually, that shows your understanding of the process, and that shows that you are being careful when it comes to modeling. So, keep that in mind. These are some of the commands, relevant commands in R. Whatever practical guidelines I have talked about, they are best understood by way of implementation.